Hey, physical science students, Mr. Lambert here. Miss Wood and I hope you had a fantastic Easter weekend, and we're going to start the week with a quick tutorial on the start of Lesson 9, Chapter 3 in your text, which covers pages, for Section 1, covers pages 72 to 79. I'll do a quick little lesson on forces, the introduction to forces, friction, gravity, and weight. So I'm going to pause real quickly so I can show you my board, and we'll start forces. Okay, as defined in your textbook, a force is a push or a pull. We talked last chapter when we dealt with motion. We know that things move, but what causes things to move? The reason why objects move is because of forces, these either pushes or pulls. First off, I want to talk units. A force is measured in something we call newtons. We give credit to Sir Isaac Newton, who understood motion and gravity, and we give him credit for understanding and progressing this science. So we measure forces in newtons, and the symbol for Newton is a capital N. On page 73 of the text, there's a picture that describes people pushing and pulling on a box on the floor. And so what I've drawn here is a couple arrows showing the size of the particular force acting upon an object. So you'll read that there are forces, and we can call them balanced or unbalanced forces. And we also have a term called net force, which describes the total, the sum of all of the forces acting on an object. The first example on page 73 shows two people pushing on a box to the right hand side. And so you have a person pushing to the right, and you have another person pushing to the right. If you add up both of those forces, you have what's called the net force. Notice I made the arrow longer to show that there's more force if we add the two forces up in this particular direction. This is what's called an unbalanced force. Everything is going to the right, and that's going to make the object move to the right-hand side. The next picture on page 73 shows a very large force, someone pushing with a lot of force on the box in the right-hand direction, but there's someone on the other side pushing with a smaller amount of force in the other direction toward the left-hand side. As you can imagine, this force in the right-hand direction is much greater, more newtons, more force going to the right-hand side than the left-hand side. So if you add these two forces together, the net force is still going to be a small amount of force in the right-hand direction. The net force is still considered to be unbalanced, and it is going to make the object move. It's going to make the object accelerate in the right-hand direction. The last example on page 73, I tried to draw the arrows with the same length, the same magnitude. You have a force pushing or pulling in the right-hand direction, and then opposite that, you have a force in the other direction, the opposite direction, with the same magnitude. Let's just assume that these are the same forces going in opposite directions. So what you'll have here is a net force, the sum, the total of the forces of 0. So what we have here is a balanced force, total force of 0. The object is not going to move or accelerate in any direction. Okay, the next topic that's covered in section 1 of this chapter is friction. It starts on page 74. Friction, according to your textbook, is defined as the force that opposes the sliding motion of two surfaces that are touching each other. Friction serves to slow down the motion of objects. There are 3 types of friction that we want you to be aware of. The first is static friction. Static friction, I'm going to use my hands as an example here. Anytime you have two objects in contact with one another, even if they are not moving, they are going to encounter static friction. Think of the smoothest surface you can, whether it's glass or a mirror. If you think about it at the microscopic level, the atomic level, there are still lots of imperfections among the composition of these molecules, these surfaces. So they're never going to be perfectly smooth. There's always going to be some sort of friction between them, and that, of course, is static friction. That again is on page, let's see, 74. It talks about micro welds. As smooth as you could have two surfaces, there's still going to be imperfections, and there's always going to be some resistance when they are touching. When they're not moving and two objects are in contact, that is static friction. Again, friction is a force, it's measured in newtons. That's static friction. Sliding friction is when two objects are actually sliding past one another, like my hands are moving now. It takes a little bit of force. It takes some pressure, a push or a pull to make these two objects slide past one another. And as they are moving, they are encountering what we call sliding friction. The third type is rolling friction. Think about roller skates, roller blades, or tires on a vehicle. Even though they're rolling in a circular motion, they're still coming into contact with another surface. Two surfaces are still touching, so they're going to encounter what's called rolling friction. Rolling friction, as it deals with cars, we use the term traction. And as most of you know, in the winter in New England, we want lots of traction on those tires. Next is gravity. Next up on page 76 is another force that we call gravity. It's considered one of the four fundamental forces in the world of physics in the universe. Gravity is misleading for many students. Most people think gravity and stuff goes down. Well, that's not really what gravity is. We know as things going down because of where we are in the universe, and I'll talk about that. But the definition of gravity is this: an attractive force between any two objects that depends upon these two following things. It depends upon the masses of the objects, how heavy they are, and the distance between them. There's an equation that's given in the book, but we want you to understand the concept of gravity and how it relates to mass and distance. I tell my students this: imagine you're in deep, deep, deep outer space, far away from any planets, any stars, and you get two, you can see this, two basketballs, and you just slowly let them go. Gravity is a force that, because it's an attractive force, it's a force of attraction, the two basketballs would slowly, eventually come together. That's what gravity is. Why do we think of gravity as things going down? Because any object that we deal with on a daily basis has to interact with the heaviest thing, the most, where is it? The most massive object that we encounter on a daily basis, and that's planet Earth. So when I drop a pen or when I drop a paper clip or whatever, that object is going to gravitate. It's going to be attracted toward the most massive object that it's closest to, and that is planet Earth. But please keep in mind, gravity is a force of attraction. It's not down. Don't think down. It's a force of attraction between two objects, also measured in newtons. Okay, the last topic starts on page 78, and it discusses weight. One thing we want our students to truly understand is that weight is not the same thing as mass. Let's do the definition first. Weight, the definition of weight is the gravitational force exerted on an object. So something's weight depends upon how much gravity there is. So it depends upon where that object is in the universe. Like I just said, weight is not the same thing as mass. We always talk about when you speak with your friends, you say, "Hey, how much do you weigh?" Well, what we really should be asking is, what is your mass? Because even though we're all on planet Earth, mass does not change no matter where you are, but weight does based on where you are, based on gravity. Here's what I've done. Mass, the unit for mass is kilograms. The standard unit for mass is kilograms. The standard unit for weight, because again, weight is a force, because that's what this section is all about, is measured in newtons. I want to direct your attention here because we're all on planet Earth and the majority of us are never leaving this planet. The force of gravity on Earth is 9.8 newtons for every single kilogram. Okay, so here's an example of what would happen uh, for our weight based on where we are. I have an example here of the Earth versus the Moon. If and by the way, the average human has a mass, not a weight, a mass of 50 kilograms. If they have a mass of 50 kilograms on planet Earth, if we were to multiply that by 9.8, 50 kilograms by 9.8 newtons, which is the force of gravity on planet Earth at the surface of planet Earth, they would weigh 490 newtons. They would have a weight of 490 newtons. Okay? If that same person, that same 50 kilogram person went to the moon, their atoms wouldn't change. They would have the same composition, so they would have the same mass. But because they were on the moon and there's less gravity on the moon because the moon is smaller, and remember, gravity deals with mass and distance, and the moon is much less massive than the Earth. That same 50 kilogram person on the moon, if you multiply 50 by 1.62, I had to look that up. That's the gravity on the moon per kilogram. That same person would weigh 81 newtons. So notice, depending upon where an object is, their weight or the object's weight is not necessarily going to be the same, but their mass is. No matter where you go in the universe, your mass will be the same, but your weight in newtons, because it's a force based on gravity, will change. I hope that helps, and we will talk to you soon.